Hello, good morning in Bogota, good afternoon in Europe, and good evening in Australia. My name is Santiago Vargas, and I will be coordinating this session in which we will have the thesis presentation of the student of the National Astronomical Observatory, Itamar Alfonso Lopez-Trilleras, to obtain the master's degree in Sciences Astronomy at the National University of Colombia. The title of the work is Reconstruction of Mass Profiles in Disk-like galaxies based on its properties of lensing and rotation curves. The thesis advisor is Professor Leonardo Castañeda from the National Astronomical Observatory. We want to thank and welcome cordially our jury members, Dr. Rachel Webster from the University of Melbourne in Australia, and Dr. Frederic Courbin from the Swiss Federal Institute of Technology in Lausanne. Thanks for your presence today, and also thank to all the people attending this presentation. The rules for today's presentation are the following. Our student has 40 minutes to present his work, followed by the questions from the jury members, Dr. Rachel Webster and Dr. Frederic Courbin. After that, questions are open to the audience, and the thesis advisor, Dr. Leonardo Castañeda, will have the opportunity to ask and comment on the work. The session will close with the jury deliberation and the announce of the final decision and comments. Once again, thank you very much for being here today. Please, Itamar, let's share your screen and begin your presentation. Thank you very much. Aún no la vemos.
I cannot share the screen. Okay. Now.
Okay, yeah, so 40 minutes from now. Thank you.
Thanks. With regard to all, my name is Itamar Alfonso Lopez-Trilleras. My professor at Webster is the PhD Leonardo Castañeda, Colorado. This work is presented as requisite for degree master in astronomy, science astronomy in Observatory Astronómico Nacional, Universidad Nacional de Colombia. And the title of this work is Reconstruction of Mass Profiles in Disk-like Galaxies based on its properties of lensing and rotational curves. Well, the contents of this presentation is next, is the motivation of this work, the methods of mass reconstructions used in this work, the importance of combination lensing and galactic dynamics. Is presented the codes Garland Spy and Garland Spy. Is presented the mass reconstruction in galaxies J2141 and J1331. And with Garland Spy is present the mass reconstruction in quasar HE0435 1223. Finally is the conclusions and events and publications of this work. Well, in first time is the motivation of this work. It's very important to highlight, as in the mass reconstructions in these like galaxies are present two methods which are taken into account in this work. One of these methods is the rotation curves, which are a method based on galactic dynamics with Newtonian gravitations. And the other method is the gravitational lensing effect, which is based on general relativity given by Albert Einstein. And the objective of this work is take these methods and made the combination and tested of BAT with the restrictions that BAT can give us for this purpose. Okay, for this reason, these methods of mass reconstructions is very important to highlight that the components of the galaxies of disk have these mass of distributions. In first time is the bulge. We have the galactic disks, the stellar halo. These components for the now baryonic matter, and in other hand is the dark matter halo in these components. It's very important to note as these components regarding to galactic dynamics interacts while the Poisson equation, which due to the linearity of this relation, it is possible that we can the possibility of express the total density, volumetric density, gravitational potential, and circular velocity as a superposition of each component of mass. And an illustrative example is the case of the galaxy NGC 6661 present in this slider, with where for the observational data we can the possibility of make the fitting track of a superposition of the components. The green line, which belonging to the dark matter halo, the red line, which is the galactic disk, and the green line, which is the bulge. Fine. Regarding to the other method of mass reconstruction is the gravitational lensing effect, or GLE. It is very important to note as in this method we can the observationally image generate track of the GLE. This image belonging to a background source, and with these coordinates we made a fit based on lens equations. This lens equation is illustrated in the slider, where we have the beta variable, which is the coordinates of the source. We have a theta as the coordinates of the image, and it's this other third C, which is denominated the deflector potential, and is very important for this work because in this term is implicitly the information of the lens, and we take mass distribution with a spherical symmetry, and for these profiles is possible express the potential deflector track of the equation 3, when in this relation is the term kappa, which is denominated the convergence. This convergence is defined as sigma over sigma critics, where sigma critics has implicitly the cosmological distance, and in other hand is the sigma, which by means of the equation 2, it is possible express as a superposition of H mass distributions with its contributions. Okay. These methods of mass reconstruction in this work are illustrated in this slider as these methods taking advantage of distinct geometrics. For example, in the case of the GLE, we made the mass projected along of a cylinder, where each cylinder it's within a radius equal to the Einstein ring or the critical curve. And in the case of the galactic dynamics, since the velocity of rotation, we established a geometry in which we made the projection of mass through distinct spheres with distinct radius, and with two distinct geometrics. In this work, we establish distinct restrictions for the mass reconstructions, and for this reason, the purpose is taking advantage of these restrictions and made the combination for the mass reconstructions. Fine. For this purpose, we in this work developing the Garland Spy Code. This Garland Spy Code is a computational routine developed in Python. The purpose is makes the mass reconstruction based on lensing, where in the case of the lens plan, we established a grid of 100 by 100 points. And with this code, it is possible obtain the inverse numerically of the lens equations and make the estimation in the position of the source. This when we has the coordinates of the image. And for this reason, we established for Garland Spy the main libraries. These main libraries are NumPy for the case of data handling. It's Matplotlib for graphic interface, MC, and Corner for Bayesian statistics in the parametrics exploration, which allows obtaining the parameters and its uncertainties belonging. In case which we made the test of Garland Spy was with the analytical solution for the isotherm singular sphere profile given by Hurtado. When in this case we established a values for the lens and the source. We, for example, in the case of the sigma, which is the dispersion velocity in these profiles, we established these values, and we modeled a circular source with radius r and center h and k, establish these values, and with a Euclidean focus, we established these values of distance observed source equal to 2 kiloparsecs and distance lens source equal to 1 kiloparsecs. We obtaining with this analytical solution the image, the formation of image illustrated in these sliders, and with Garland Spy was possible obtaining this same image. This image is very close to the analytical solution given by Hurtado, where the percentual error is very low, is a ln of 0.1, and this is a great result. The same occurs in the case of compute of deflector angle, and with the case of deflector potential for these profiles, and this allows obtaining credibility results for the case of lens equation with Garland Spy. Okay, however, it is very important to highlight that the CIS profiles is not the unique profile that with Garland Spy the user has the possibility of work. This because for this mass distribution, the user has distinct options. For example, in the case of Dark Material, the user has the possibility of work with different profiles on bucket profiles. In the case of the galactic disks, is two possibilities: exponential disks and Miyamoto-Nagai profiles. And in the case of bulge, we take the possibility of choose the Miyamoto-Nagai with two range of parametric explorations. With this mass distribution established the range of exploration for the parameters illustrated in this table, where it is very important to note that H values, H parameters range was taken of distinct works given by other authors regarding to dwarf galaxies and galaxies very similar to the Milky Way. And with taking these values for the parametric explorations, and we applied this while the Bayesian statistics. For these Bayesian statistics, with Garland Spy, we take the advantage of the Metropolis Hastings algorithms, where binding of the Markov Monte Carlo chain with Garland Spy, we was established this MCMC. It is very important to know that Garland Spy is focused in compute two terms. One terms is the now likelihood, and the other terms is the priori. In the case of the likelihood, with Garland Spy, we established function minimization functions, which we made the comparison between the observational image and the image belonging to a parameter set with a specific model of length. And it is taking it into account the error in age coordinates of this image. This allows us obtaining the initial guess for the MCMC. We make these multiparametric minimization functions in all parametric range by quartiles, and this allows obtaining the initial guess for the MCMC. With this initial guess, the chain is beginning to run, and the compute of the likelihood is made with Garland Spy with these same minimization functions, but with Gaussian distributions, where it is very important to highlight that in this case we include two producers because we have assumed that it is possible have distinct source, and with a number if or a source, it is possible that this number I of source we take a number j of image, and for this reason the two producers are included in this case. Additionally, is the compute with Garland Spy of the prior, where these values is very easy. In this case, if the parameter set is within of the parametric range that the user can explore, these values is 1, and in other case, these values is 0. Okay. Of this manner, we take this process flow diagram, where it is possible evidence the algorithm that Garland Spy take for this process of parametric explorations. In first time, we obtaining parameters of the lens model, Garland Spy determination the cosmological distance track of the solution that this code made to the Dirac equations for cosmological distance. Next, the user has the possibility of define mass profiles for each galaxy components, and with these mass profiles is compute the deflector potential for ice mass distributions, and next is the superposition of all deflector potentials for obtaining the likelihood. This likelihood made the parametric exploration with the MCMC, and this allows obtaining the set parameters belonging to this galaxy. Okay, an illustrative example of how as Garland Spy procedures in this parametric exploration is applied the case of cis profiles. And we made this comparison. In this case, is very important established values of the length and circular source, which are illustrated in this sliders, with these values of cosmological distance, again as Euclidean focus in this case. In this case, with these values in the cis profiles, it is possible obtaining this image belonging to this circular source. And the objective with Garland Spy is that we will to assume that we don't know the original values, these values of the lens and the source. We supposed that we alone know the values of the cosmological distance, and we alone know the values of the coordinates of this arc in the side right up. In this way, we don't know the values of this arc, and these don't know the values of the source. And the purpose with Garland Spy is obtaining these values that give us the possibility of obtaining this arc generated with Garland Spy. Fine. Um, for this reason, we established this parametric range for each parameters. And it is very important to note that Garland Spy give to the user the possibility of choose the number of walkers and steps that he like applied in the chain, in the Monte Carlo Markov Monte Carlo chain. In this case, we applied a number of 100 walkers with a number of 1,000 steps, and for the compute of the initial guess, we obtaining this are generated with this set of parameters with this source. Although this initial guess with this arc is not close of the original arc, are not close. However, with this initial guess, we began to run the MCMC, and it is very important that we take the possibility of seeing as these chains present a convergence from the steps 400, and this convergence, the values is very important, and this same behavior is in the other parameters, where and for this reason was possible obtaining these contours with the values illustrated in this table with its uncertainties. It is very interesting evidence as with Garland Spy was possible obtaining these values which are in concordance with the original values established for this arc. Fine. In this slide, there is illustrated the source obtaining while the parametric exploration, and the arc obtaining with Garland Spy, which are in concordance and very close to the observational arcs of this illustrative example. Fine. Other job that Garland Spy give us obtaining is the compute of the critical curve and caustic curve. This is with the method proposed by Bartelmann for a grid, and in this case, for these cis profiles, was possible obtaining this critical circle, which is in concordance with the critical circle obtained by Hurtado in its analytical solutions, and with and if we apply the lens equation, we can obtain the caustic curve, which in this case is a point, a caustic point. Fine. The other code for this for this work is Galrod Pi. Galrod Pi is a code developed in Python by distinct members of gravitation group of the Universidad Nacional de Colombia. This Galrod Pi code is based in mass reconstruction with galactic dynamics, specifically with rotation curves. Galrod Pi has the same potentials and values range of Garland Spy. This is a great advantage because with this we have the possibility of complement Galrod Pi with Garland Spy, and therefore the lensing with galactic dynamics. An advantage of Galrod Pi is the possibility that the user has of evidence age gravitational contribution of the galaxy, and also is the possibility of made made the fitting visual of the parameters for the case initial in the MCMC. The main libraries of Galrod Pi are very similar to Garland Spy, but in this case we include AstroPy for the case of astronomical units and data handlings, and include Galpi, which are a package very useful in the case of compute rotational curves and gravitational potentials. Okay, the Bayesian statistics with Galrod Pi is very similar to Garland Spy. Along that, in this case, the compute of the likelihood is more easy. In this case, we include the data of circular velocity and the values of the model for circular velocity with a parameter set and the error in each observational data. And the computational cost in this case with this Gaussian distribution is very low in comparison with the computational cost of Garland Spy. Fine. In this slider is illustrated the graphic center of Galrod Pi when the user has the possibility in this panel of the said left up of choose the potential that he like use it for the mass reconstructions, and next is the sliders which the user has the possibility of make the parametric adjust for the obtention of the initial case, where in the right side it is possible evidence as for observational data of circular velocity. We have the possibility with Galrod Pi of make the superposition of distinct potentials and gravitational potentials and obtaining this fitting. Fine, and case which Galrod Pi was tested is the case of M33 galaxy, where this observational data of velocity, of circular velocity, was fitting, taking into account two profiles, the narrow frame width for the case of dark matter halo, and the exponential disk for the case of all baryonic matter. In this case, what's possible obtaining these contours, and it's very interesting to watch us with these values of circular velocity. It is possible made the estimation of mass. These values are therefore in concordance with the values obtaining by Lopez, Fuon, and collaborators regarding to the stellar mass and dark matter halo. And this work was applied other methods of luminosity and other techniques. Fine. With these two codes, we applied these codes in the mass reconstruction of these galaxies. In first time is the galaxy J2141, which is a galaxy of type is 0. It is very important to know that this galaxy present the lensing effect, where was possible obtaining of Newton and collaborators. These are generated in its model of lens, and in this case, with Garland Spy, we applied the mass reconstruction based on its arch belonging to a background source, where for a computational cost low, we work with the contours of this arc. We, with Garland Spy, made a routine for the discrimination pixel to pixel, and with this, we call obtaining these contours. However, since the noise of the image the contours are not completely, but however, with these contours, what's possible obtaining the agreed result. And regarding to the rotational curves, Dutton and collaborators give us the values of circular velocity, since the inclination of spectral lines. And for this reason, we take the possibility of applied Galrod pi and Garland Spy. Regarding to Galrod pi, it is very important to note that as to we evidence in these sliders, the convergence of values in these chains is not a great convergence. And the same occurs in the case of Miyamoto-Nagai profile for the case of bulls. Is not a convergence of values. However, sorry, in the case of exponential disk, these values yes present a convergence. This is a problem. This problem was denominated by Dutton and collaborators as the degeneracy problems. These problems is caused because of the gravitational dominance of disk, and it was possible evident with Galrod pi. These show us it is an interesting object because this has gravitational dominance, the baryonic matter, and is not common because generally is the dark matter allow the gravitational dominance. For this reason, in this system, here is difficult to know the gravitational contribution of H mass component. And for this reason, in this work, we applied the combination of Galrod pi and Garland Spy because we have a restrictions given by the interactive fit with Galrod pi. These restrictions allow us applied in Garland Spy for the mass reconstruction and made this combination of geometries and restrictions allow us obtaining this mass reconstruction. For this reason, with Garland Spy, in the case of the arch, we applied a cosmological model lambda CDM. And with this cosmological model, what's possible obtaining this value for distance of cosmological distance. Next is the model of the source. We modeled a circular source in the formalist strong lensing, and was possible obtaining these values of this source, where the source is very difficult to distinguish in comparison with the arc, and for this reason the magnification is very important in this case. Fine, with the restriction of the source, the restriction of cosmological model, the restrictions given by Galrod pi was possible obtaining this convergence of values. These values converged in this case for the case of the narrow frame Watt profile and in the case of Miyamoto-Nagai profiles. And for this reason, what's possible obtaining these contours illustrated in these graphs. Fine. With this, the fitting in the case of lensing and rotational curves is illustrated in this case. It was a fitting of bad observational data, and this is a great. And the parameters obtained are consigned in this table, where with these parameters was possible computed the critical radius and the Einstein radius, and these graphics are shown in this slider. Fine. For this reason, we take the possibility in this galaxy of establishing the enclosed mass in three radius. The critical radius, the Einstein radius, and the radius within the rotational curve. It is very important to note that in the case of the baryonic matter within the rotational curve, these values in this table is in concordance with the values obtained by the two collaborators in regarding to this work. Along that, in this case, we applied Garland pi and Garland spy and no luminosity methods as they has the possibility of applied in its work. Fine. And for this reason, we estimation the mass of bulge, this and their material as illustrated in this slider. Fine. The other galaxy is the case of galaxy G1331, where it is very important to highlight that it is an object very interesting because this galaxy present the gravitational lensing effect through a quadruplet of images. This four images belonging to a background source, and also it is very important to highlight that this galaxy present supermassive and counter-rotating counter-rotating core, and it restricts this made this with this is very difficult apply Garland pi in the inner region of this galaxy because the negative values of the circular velocity, and for this reason we applied in this inner region Garland pi due to the lensing effect in this region of the galaxy, and in the peripheral region we applied Garland pi for this mass reconstruction. And of these four, with a cosmological model lambda CDM, we can obtain in these values of cosmological distance, where we made the model of punctual source with a strong lensing formalist. With this, we take the possibility of obtaining these values of the source and these values of the mass reconstruction for this lens. It is very important to highlight that it was obtained with along 4 points of the image, and the contours are present in this case. Fine. The fitting obtaining of the between observational image and image of the model is illustrated in this slider, where in this case was possible obtaining the critical radius, the Einstein radius, the caustic curve, and with this, we with Garland spy established the enclosed mass within the Einstein radius and the critical radius. These values with these 4 points with Garland spy was possible obtaining values in great concordance with other values obtained by other authors, where we take the possibility of alone work with this image and not with luminosity of the galaxy, and however the values are in concordance with that reported by other authors. Fine. In the peripheral region of the galaxy is the case of Garland pi, where these contours are presented in these sliders, and in this case is very important to highlight that we have along 3 points of data of circular velocity, and with these 3 points we take the possibility of obtaining this mass reconstruction, and we obtaining the gravitational dominance of the bulge, which with along 3 points is great because it is in concordance with the observations. Find within this radius belonging to the rotational curves was obtaining the values of baryonic matter, bulge mass, and this is in concordance with the obtaining by Dutton and collaborators for this case. Of this galaxy, for this reason, it is possible to conclude that about of the 78% of the mass is enclosed in the critical radius. Is confirmed the presence of a supermassive core, and it is important the possibility of explore Garland pi with Jean's equation. This because in the case of negative values, we cannot apply Garland pi. Fine. Finally, is the quasar HE0435 2023. 1223, sorry. In this slider is presented the image given by Courbin and collaborators, where it is very important evidence the formation of Einstein ring. In this case, we applied Garland Spy for this quasar, for the mass reconstruction of this quasar with a cosmological model lambda CDM. We obtaining this cosmological distance for a quadruplet of image belonging to a background source. In this case, the fit is illustrated in these sliders with these parameters. And in this case, we obtaining Einstein mass in concordance with the values reported by other authors, Courbin and collaborators. And regarding to the baryonic matter fraction, these values obtaining with Garland Spy is in concordance with the values obtained by Courbin and collaborators when they applied the initial mass function of Zapelter. Fine. In conclusions for this work, was presented Garland Spy as an efficient tool for mass profiles reconstructions. In other hand, it is very important to comment the great advantage of combined lensing and galactic dynamics. And in this work with Garland Spy and Garland Spy, these tools very powerful. It is very significant. It's very important to highlight the significant results that we can obtain with a mass model with spherical symmetry. And in future improvements for Garland Spy is a number major of mass profiles. We like work this code with mass of superficial of fringe and temporary cosmological delays for the estimation of Hubble parameters. Fine. Finally, is the advantage of performing visual fitting in these routines for the case of the initial guess, and this is we like work in obtaining these fitting interactives with Garland Spy. Fine. And events and publications. This work was present with 2 posters in Congresos de Colombiano de Astronomía, COCOA, with 2 posters. And it's very important to highlight that Garland Spy has a publication with the Journal of New Astronomy, and in this moment Garland Spy is prepared. It is prepared for this same journal. The repository is public with Garland Spy is in GitHub, and this is the main bibliography of this work. Finally, I like hand over the mensch to God, life and the life for that give me the opportunity of the end this work, to my wife for fighting with me and cheering me on, to my father and mother for their unconditional support, to my sister Ruth for her excellent company, to my sister Juliet for believing in me, to Professor Leonardo for his infinite patience and great friendship, to the OAN and the Faculty of Science for their financial support, Beca Auxiliar Docente, to Islena for all her help. Finally, in dedication, I like dedicate this work to my son Juan Felipe, that gravitational lensing that magnifies the light in my universe. Thanks.
Okay, thank you very much to our student Itamar Lopez-Trilleras for the presentation and also for keeping it within the time schedule. Now the session continues with the questions from our jury members. So please first, Dr. Rachel Webster from the University of Melbourne, I invite you to activate your camera if you want and start sharing your questions. Thank you.
Okay. So Itamar, that was a very nice talk. So thank you. And thank you for describing your work. The first question I wanted to ask you was, quite often we think there may be other masses along the line of sight to the primary lensing galaxy. Have you thought about whether or not that might be important in the modeling, and if so, what effect it would have?
Okay.
Did that?
Sorry, if the values of masses are correct, is the question? Sorry.
So you've given us a lovely model of the main galaxy, right? But sometimes there might be other masses along the line of sight to that galaxy. That's the main one that's doing the lensing.
Yes, teacher. This is a agreed question because we consider that it is very important to consider the external shield, for example, because this allows obtaining a best analysis of this mass. However, we take the advantage of these galaxies when these values was necessary with the values of mass of the galaxy, but it is very important to include this other mass with external shear. Yes.
And is that something you can easily do, or in your model?
In this model, fine. We include the shear of the model of mass, but not are included the values of external shear. We have work in this external shear. However, with the initial purpose was working in the mass belonging to the galaxy.
Okay, no, that's fine. Frederic, do you want to ask a question now? I mean, I have some others I can ask, but would you like to?
Well, if you want, we can do one each. Or
Yeah.
So actually, the line of sight was one of my questions, but another one would be, well, just you put numbers a bit everywhere, so like velocity dispersions, distances, and in your toy models at the beginning, and also somewhere in the middle of the talk, you have velocity dispersions in toy models around 1 kilometer per second, or sometimes 10,000 kilometers per second. But does it sound reasonable to do such toy models, or are you familiar with such velocity dispersions?
Sorry, the question is about of the dispersions of.
Yeah, because you have toy samples where toy models or toy whatever examples with sigma equal 100 kilometers per second, and then after you explore a range of tens of thousands of kilometers per second. So what is the typical velocity dispersion of a lens?
Yes, dispersion related to observational data or values.
Yeah, if you point a real telescope to a real lens, what typical number you would get?
Oh, okay. this is related directly with the image. For example, in the case of this of this galaxy, the galaxy G2141, the errors was taken of given by Newton and collaborators in its model, when its error is in pixel, is of one pixel for each values. And we made the discrimination of and it's obtaining these coordinates, and we take the conversion to arcoseconds. In the case, for example, in the quasar, in this quasar, these values of the zeros was taken of the Courbin work regarding to the dispersion of position in each image.
Yeah, but no, the question was more about what are typical values for stellar velocity dispersions in lens galaxies. So, for example, the one you show.
Yes.
You have an idea of the orders of magnitude?
Yes, no, the Galrod pi is made initially for the case of circular velocity. The dispersion velocity in this case are not are not values that with Galrod pi we take the possibility of work where we with Galrod pi work along with these values of velocity, circular velocity.
I don't know. Can I comment a bit? It's only a comment.
Yeah.
Maybe Tamar, can I translate to Spanish the question? Maybe he's a bit nervous.
Si quieres puedo seguir en español.
Yeah, but Professor Rachel, I mean, I can translate and he can try to in English.
Okay.
Itamar, ¿cuál es el valor típico de las velocidades de dispersiones estelares? Sin programas ni nada, sino típicos en las galaxias.
Ah, ok.
Trate de escuchar, tranquilo, trate de escuchar la pregunta. Yo sé que cuando uno está, su primera charla es en inglés.
Bien. Gracias, profe. La pregunta es entonces los valores típicos de velocidades de dispersión en las galaxias.
Sí,
¿Sí?
pero en English. In English.
English.
Try to answer in English.
Yes.
Because
This is a value that in this moment I not remember these values.
things in the velocity of the sun in the Milky Way, more or less.
El Sol en la Vía Láctea.
The velocity of the Milky Way.
El Sol en la Vía Láctea.
Our sun in the Milky Way.
About sun in the Milky Way. I am nervous.
Okay, maybe that's too much of an observational question, and most of the work is theoretical there. So, may I ask another one? Okay, so on these slides you show some prediction of the source positions. So you have now like a red source somewhere, and you have a number of green sources. So it looks like you predict the contours of the images, but you could very well predict the full pixelated image. Why don't you do this? Si quieres lo traduzco en español.
Because I work with the pixel image.
Uh-huh.
Yes, fine. In the case of this quasar, the values are not. However, in the case of G20, 2141, the values of coordinates of this image, these coordinates are not given by Dutton and collaborators, that give us the values of rotational velocities. And for this work in this galaxy, the work was focused in discriminate these values pixel to pixel. However, they give the correspondence between arcoseconds and pixels, and with this conversion factor, we work in this image of this manner. I don't know if I say the records are to your questions.
Not completely. So if you go back a few slides before, or if you go a few slides after that one, some more, no, more. Where you have these green and blue contours.
Contours?
Yeah, of the lensed image. Yeah, probably this one. Okay, so you have one source and a number of green images. So how do you end up with this mapping? Are the green points the contour of some bigger image, or the green dots are just what you predict?
Si los puntos verdes son puntos que dan cuenta de otra imagen más grande o son solamente los que tú elegiste.
No, these contours.
I think maybe you can ask in Spanish, and he tries to answer in English.
Bueno, sí.
But Itamar, you try to answer in English. But Frederic, can you please repeat your question in Spanish?
¿Ya? Sí. Bueno,
Thank you.
En la imagen acá tienes una fuente como roja en el centro. Y viene un montón de imágenes verdes.
Sí, señor.
Y la pregunta es saber si estos puntos verdes son como predicciones del modelo,
no,
o solo son los contours de alguna imagen que no se ve acá, o cómo funciona el algoritmo.
Okay, these contours are not of the model, belonging to the model. These contours belonging to the arc illustrated in the previous sliders.
¿Sí?
And based on these contours, Garland Spy was applied for the mass reconstructions with this source. The model with these observationally values of contours are in these sliders. In this case, yes, is the observationally data in blue and the model data, so the values of the model obtaining with Garland Spy.
Sí, pero veo la fuente que utilizas es un point source, una función delta. Y la imagen, la fuente que utilizas es una función delta, un point source perfecto.
Yes.
Y entonces, ¿cómo eso se transforma en un arco? Tienes que suponer alguna forma, algún perfil por el fuente.
Yes. The source is a circle, and we made in this case the assign for this source based in the positions of each point in the arc. We ask a correspond coordinates of this circle with the arc. For example, in the half of this arc is the origin of the source, and source in an angle equal to p radians. And h points based on its positions throughout of this arc has the possibility of make the belonging to async to h to h point of the source. This was the method for asking this
Okay.
value.
Ok, bueno. Bueno, ya quité mucho tiempo a Rachel. Yeah, sorry. So Rachel, if you want to ask another one.
Yeah, I was actually going to ask another question about exactly this graph, because I was very interested to see that your fit gave a very small mass contribution to the bulge in this fit, which I thought, which surprised me, I guess. So you've got, quite a significant fit to the exponential disk and to the NFW halo, but the bulge is actually very small. And I wondered if what the light, I know you haven't fitted the light profile, and I know that is something that you're thinking of doing into the future, but I wondered if you had looked at the optical image to see whether this was sort of looked consistent with the light distribution in the image. Does that, do you understand what I'm asking? So, I mean,
can I translate?
Please do.
Ok. Itamar,
Yes.
la contribución del bulbo en este fit se ve muy pequeña y la mayor contribución está en el disco exponencial. La pregunta es si usted miró la posibilidad de tener una imagen óptica para mirar si el bulbo es así de pequeño o no. Entonces, pues la pregunta es si tenemos esa imagen óptica o no tenemos esa imagen óptica.
Not we have not this image. The unique image of this galaxy is the illustrated in this slider. In this case, we had the photographs takes by the telescopes Checks and Hubble.
Mhm.
And in the case of the work of Newton, they not study the contribution of the bulge. They alone work with the dark baryonic matter, and however they speak about of the great contribution of the disk. This is the unique that they speak about of the distinction between bulge and disk. And we made this estimation of contribution of the bulge of Galrod pi in this case, but we cannot we cannot obtain the image of this pulse, to difference of J1331 where this image was possible obtain.
Is there any other questions from our jury members?
Maybe
Comments?
I would have a very general question, so maybe provocative question.
Okay,
Yeah.
You know that
they are welcome.
on the market, there is this Astronomy package, which is super flexible, doing MCMC of everything, and even combining in a joint Bayesian analysis the dynamics and the lensing. So why just you didn't use this? If you want, I translate. So if I translate, it's Tal vez sabes que existe un software que se llama Lenstronomy.
Yes.
Mm.
In this case, we began using Lenstronomy, and in the case of the lens equations and the Bayesian statistics, we applied Lenstronomy. However, the purpose was made the combination with rotational curves and the codes Galrod pike present and gravitational potential distinct to Lenstronomy. For example, in the year 2018 and 2019, 2018 specifically, Lenstronomy in this moment hasn't not include the Miyamoto Nagai profile. Um, and the number of walkers and steps for the case on the MCMC are not possible in this moment include for the Bayesian statistics. And for this reason, um, we take the necessity of include and developing other code. And however, Lenstronomy was very useful for that we can test Garland Spy. In the case of narrow frame wide profiles, we made the comparison between the image format of Lenstronomy for distinct values, and these are in concordance with Garland Spy. And for this reason, Lenstronomy was not in this moment included because the profiles and the MCMC are not very similar to Galrod Pi.
Yeah, but it's easier to, because Lenstronomy is open source, so it's easier to write a module in Lenstronomy than to write everything again.
Yes.
I'm not complaining about it. It's just ourselves here we make developments on lens models, and we code everything within Lenstronomy to avoid reinventing the wheel. On the other hand, it's nice to have independent codes as well. So no, it's just, I'm not criticizing there. I'm just maybe suggesting that you can save work by using open source and well-tested code. Anyway, nothing bad.
Okay, we have chance for more questions of our jury members. You've done?
I'm happy.
Okay. Okay, so if there are no more questions, I would like to thank, on behalf of the members of the National Astronomical Observatory of Colombia, our jury members, Dr. Rachel Webster from the University of Melbourne in Australia, and Dr. Frederic Courbin from the Swiss Federal Institute of Technology in Lausanne for their questions and comments. And now the thesis advisor, Dr. Leonardo Castañeda, will have the opportunity to ask and comment on the work.
Yeah.
So I invite you to activate your camera if you want and start your comments.
Okay.
Thank you.
Maybe I am really dark.
In the darkness.
Somehow.
Okay. Okay.
I
No
want
problem.
to say thank you very much to both professors. For us, it's very important that real expert people read the work. And yeah, I have only some comments. I think that we start to check Lenstronomy, but also different to your institutes. In our institute, we are building a school in astronomy. That is very different only to do research. Itamar is teacher at the secondary school, and he takes really big effort to try to understand all this stuff of lensing, MCMC, all these things. I mean, I only comment to you because, for example, for us, it's really kind of dream to have observations 20 years ago. Yeah, when I was in Bonn, sorry, but observations was kind of privileges for some people and not for everybody. Today, we have really the opportunity to do some astronomy from here. And it is the purpose also to write the new codes. I mean, you can't say, of course, you have really, really good codes and a school for, no, I don't know, 40 years, astronomy, and these people, Jean-Paul Knight, or something, with really good lensing codes, but also we need here in Colombia to build our own codes because we need to learn how it works, this field. It's only it's one of the big purpose of this work also. I mean, for me, I am very happy because in the sense that Itamar really face very good the work. It's not easy. Go to the school, teach, go to the observatory and try to do something in 2-3 hours in the afternoon and reach really this level of comprehension of his work. I am not saying that we are not able to do really good research, but it's different when you have only people dedicated to research and people that try to understand and do something with this. For this reason, I am really congratulates to Itamar, and we need to follow to the next step with other students also. It has been more or less 10 years of trying to teach some galactic dynamics, some lensing, some cosmology, and now we are reaching some results that is very good for us, you know. And also I am really grateful with the referees because I know about your time, but also your expertise, and for us it's very important that you accept this challenge and try to understand between Spanish, English, and all these things. I mean, thank you very much. And yeah, for example, the next step that we want to try is try to prove modification of gravity, for example, FAR theories with lensing, and will be a really long way, I think. But now we have this chance. I mean, it's not only matter of we are on my, for example, my profile is quite theoretical stuff, but now we, as I say before, we can use some data and try to do the kind of work that is really important for us. Thank you very much. I don't have more questions to Itamar. Thank you, Itamar, for
Thanks.
this talk and for this big effort. And yeah, and thank you for to everybody.
Well, thank you. Yes, thanks also for the note about the working conditions of Itamar. You know, I know quite well the general situation in Colombia, so I perfectly see the challenge.
Thank you.
Okay.
Yeah. Thank you. But sure that we are improving, and in the next future, near future, we will have more. Actually, we have really good students that they are now doing astronomy in some places around the world, and even that we don't have the full amount of money, but we have really good students and people that they want really to do astronomy. For example, I had a student, Luz Angela Garcia, and she was in Australia for her PhD, and he's a really good teacher now, and she enjoys astronomy, and she enjoys cosmology. Okay, it's how we can grow our astronomical community here.
Yep.
No, you know, I mean, this is exactly how you have to start doing it. And as you say, you do it from first principles. It's a good way to go.
Thank you, Professor Rich.
Okay, thank you very much again, Dr. Leonardo Castañeda, the thesis advisor of this work, and also our jury members. So now it's time for our audience to ask questions if there is any. I can tell you that there are about 30 people watching this session via streaming. So I don't know if there are some questions. I will wait a few seconds to see if anyone wants to ask something to our student. Well, people are already sending congratulations, but no questions so far.
Maybe it's too early here for questions, you know.
Yeah, I know it's breakfast time. Okay, so if there are no questions, let me once again congratulate our students for the presentation and also to thank again our jury members. It's really a great effort, and we are very proud also of having you here in this session. Remember that Dr. Rachel Webster is right now in Australia. I don't know the time, but it's something like 9 p.m. possibly.
That's right.
Yeah. And Dr. Frederic Courbin in Switzerland, it's 1 p.m.
Oh, that's
Yeah.
one.
So it's lunch time for you. And in Bogota is 6 in the morning. So thanks all of you for this effort of trying to, yeah, Leo.
For the effort for everything. Thank you very much.
Mhm.
And
Yeah, it's
maybe
hard
in
to,
the next,
Have a good
in the near future,
celebratory breakfast.
yeah, sure. We can invite you here for some school or for, now the community here is growing up very fast, and maybe we can invite you for some conference after this pandemic. Thank you very
Sure.
much.
We'll be happy to join. You know, I'm in Colombia every summer in principle.
Yeah, sure. Thank you.
okay, and thank you very much to our audience, which is watching the live streaming of this session. So I will have to stop now the streaming because we will have now the jury deliberation and the announcement of the final decision. So I will stop the streaming and I will send our members here in this chat to the waiting room. So we will stay just with the jury members to deliberate, and I'll see you in a few minutes. So bye-bye to all our audience.